I selected only 2 questions from the October-November 2019 Paper 21 exam. One question covers estimation, EM waves, percentage, and absolute uncertainties. The second question covers density, force and momentum, third law of motion, and Doppler effect. Stay with me because it's a great practice review for you. The first question asks to estimate the mass in grams of a new pencil. So any value between 1 gram to 20 grams should be fine. So most of my students selected 5 grams. The second question is asking to estimate the wavelength of ultraviolet radiation. To make an educated guess, so here is the visible light from red to violet. So the wavelength of the red is 700 nanometer, which corresponds to 7 times 10 to the minus 7 meter. And the wavelength of the violet is 400 nanometer, which corresponds to 4 times 10 to the minus 7 meter. And here is the complete electromagnetic spectrum, from radio waves to gamma rays. It's a good idea to memorize this kind of range. For radio waves, about 10 to the 3, microwaves 10 to the 2nd power, infrared, visible light, ultraviolet, X-ray, and gamma rays, because it will be easy to answer any question related to estimation or the sequence of any wave that belongs to the electromagnetic spectrum. Therefore, the best estimation for the UV radiation is 10 to the minus 8 meters. Now you may be asked the opposite, to calculate the frequency. So how you do that is very simple. So you know the speed of a wave is the wavelength times frequency, and the frequency is, rearrange the equation, is the speed of a wave from the electromagnetic spectrum. All waves travel with the speed of light, or c, divided by the wavelength. So doing the substitution, the speed of light is 3 times 10 to the 8 meters per second, and have an estimation of any of those electromagnetic waves. You can easily calculate the frequency of the wave they are asking. Question 1b. The period T of the oscillations of a mass M suspended from a spring is given by this formula, where K is the spring constant. The manufacturer of a spring states that it has a spring constant of 25 Newton per meter plus minus 8%. A mass of 200 times 10 to the minus 3 kilograms plus minus its uncertainty here is suspended from the end of the spring and then made to oscillate. Calculate the period T of the oscillations. So in this question is direct substitutions of the values in this formula. So let's go. So here is, this is the mass and this is the spring constant. Evaluate the uncertainties. So the value is 0.562 and or 0.56 with 2 significant figures. The next question is asking to determine the value of T with its absolute uncertainty to an appropriate number of significant figures. When it says absolute uncertainty means that we need to add the units of the period, which is in seconds. So here we have the formula, and here is what you have in terms of data. For M, the mass is the value plus minus is uncertainty. Now this one is the absolute uncertainty because we have units. However, the uncertainty of the spring constant, or K, is given in percentage. So this is percentage uncertainty. So to make it easier to calculate the absolute uncertainty, since we have here the value of K in percentage, so let's convert the mass in percentage as well. So to calculate that, we need to write the correct format when we need to calculate uncertainties. So here is this delta doesn't mean change of. It means that is the notation for uncertainty. So the percentage uncertainty of the period is equal the sum of the uncertainties of the values or the variables in the formula. 2 pi is not a variable, is a constant number. So we are not going to add these in the uncertainty formula. So now to calculate the percentage uncertainty of the mass, all that we need to do is divide this number by the uncertainty by the value. And then we multiply by 100, so we have the percentage, which is 2. So now what we are going to do, we are going to look what's going on here. So you see that we have a square root. So if you remove this square root, so this fraction m over k, you'll be to 1.5 power. So then we need to express this half right here. So all this half need to multiply the percentage uncertainties, the variables in this formula. So then we are going to do substitutions. The percentage uncertainty for mass is 2, and the percentage uncertainty for the constant is 8. So 2 plus 8, 10 times half is 5%. So now we are going to proceed with calculating the absolute uncertainty. So how we do that? Now we need to remove this percentage. So now this is called fractional uncertainty. This here, when it's showing percentage, is called percentage uncertainty. Absolute uncertainty is when you have a unit. So right here you have an example of the mass. This here is the absolute uncertainty for the mass. This is the percentage uncertainty for the spring constant, which this is the notation. Now to calculate about the percentage, now we call fractional uncertainty. So how we do that? So the fractional uncertainty, we have to remove the percentage. So we are going to divide 5 by 100. And now this t on the denominator is going to multiply 5 over 100. That way you can add the unit. So that means that the t we calculate previously was 0.56 seconds. So when you multiply all these, the absolute uncertainty of the period is 0.028 seconds. Okay, so how we are going to write the answer? So the answer is given in this format. So here is the value of the period that we calculate, 0.56 seconds. And here is the uncertainties. So the uncertainties here calculated 0.028, but we need to follow the number of significant figures and decimal places, so we round to 0.03 seconds. So this is the final answer. And here, just show all the work that we did to get the absolute uncertainty of the period. Question 3 from the same exam. A small, remote-controlled model aircraft has two propellers, each of diameter 16 centimeters. This picture is a side view of the aircraft when hovering. Air is propelled vertically downwards by each propeller, so that the aircraft hovers at a fixed position. The density of the air is 1.2 kilograms per cubic meter. Assume that the air from each propeller moves with a constant speed of 7.6 meters per second in a uniform circular, let me repeat this, in a uniform cylinder of diameter 16 centimeters. Also assume that the air above each propeller is stationary. I want to make sure that we can visualize the air column under each propeller has a cylindrical shape. And here is the data that was given in this question. The density of the air is 1.2 kilograms per cubic meter. The speed downward is 7.6 meters per second. The diameter of the propeller, which makes the diameter of this cylinder, is 16 centimeters. And the time that this speed is constant is 3 seconds. Now that we understood the assignment, the question is, show that in the time interval of 3 seconds, the mass of air propelled downwards by one propeller is 0.55 kilograms. So here is all the information that we have, but I add something else. So the diameter of this cylindrical shape here is 16 centimeters, and the radius is 8, which is in meters 0.08 meters. Okay, to find the mass of this air column, we can use the density of the air because it was given. It's mass over volume. Great, so I can calculate the mass. But the problem is I don't have the volume of this air column. So to calculate the volume, remember this is cylindrical shape. So the volume formula, the general formula is area times height. So, and we have a problem that we can calculate the area, but we don't have the height. But we can use I know it's strange, but we can use the velocity formula, distance over time, to calculate the height, because according to homogeneous equations, so the distance is in meter, right? Velocity is meters per second, and this is seconds, so kind work things out. So let's go. So here is the distance or height of this air column is given by the velocity times time. So the velocity is 7.6 and the time is 3. So cancel second with second, and the height is 22.8 meter. Perfect. So now that we have the height of the air column, we can go back and calculate the volume of this cylindrical shape. So the volume is area times height. The area, cross-sectional area here is a circle, pi times radius squared times height. So doing the substitutions is pi times the radius is 0.08 and the height 22.8. So the volume is 0.458 cubic meter. Don't worry about significant figures at this point because we are not presenting the final answer. Next, to find the mass is density times volume from this formula right here. So the mass, the density is 1.2. 1.2. This K is not is a prefix, but belongs to the unit of mass, which is kilograms. So be careful with that. 1.2 times the volume, which is 0.458. So the mass is 0.55 kilograms. Still part of the question is asking to calculate the increase in momentum of the mass of air in A. All right, so at this moment you are kind, okay, how I'm gonna do this? Let's write down the formula for momentum. So momentum, or P, lowercase p, is mass times velocity. Do we have everything? I guess we do. So we have the mass that we just calculated, you have the velocity, and this is the momentum. So the unit for mass is kilograms, the unit for velocity is meters per second. Wait a minute. And y here is Newton second. And I'm going to explain in a minute. But for now, let me write down the final answer here, 4.2. You can say kilometers times meters per second or Newton second, but let's elaborate into this. So we know that the formula for force in terms mass and acceleration is this. And we know the acceleration is the change in velocity over time. And we know that change in velocity is final velocity minus initial velocity. Now we can multiply mass times final velocity and mass times initial velocity. Let's see how it looks like. Oh, this is not a formula for momentum. Mass times velocity, it is. So we can say this is the final momentum and this is the initial momentum. So final momentum minus initial momentum over time. So every time that you have final minus initial, we say there is a change of. So we use the notation, this triangle here. Note that we use this triangle for uncertainties. There is nothing to do with change of. It's just like a format. But here is a change of. So force is the change in momentum over time. In fact, this is the definition of Newton's second law of motion. Force is change in momentum over time. And actually, if in your test, if they ask define force, so you are going to say not the force is mass times acceleration. You are not going to say that. You are going to say the force is change in momentum over time. That's the correct answer. Now let's go back to why we have Newton second as an answer for increase of momentum or change in momentum. If you look this formula right here, so we can rearrange. So the change in momentum is force times time. Kaboom! That's the unit, Newton times second. All right, let's keep going. So the next one is asking the downward force exerted on this mass of air by the propeller. And note here, the momentum of the air increases in the downward direction. So the propellers push air downward, giving the air momentum. The push also gives the drone an equal upward force, so it hovers. All right, I just need to get off my chest. Now we are in this formula right here, right? We need to calculate this force, this downward force. So we are going to use the change in momentum over time. So the change in momentum we calculate was 4.2 Newton seconds, and the time that is doing all the hovering is 3 seconds. So the force is 1.4 Newton right here, kaboom. Now, state the upward force acting on one propeller. So the drone is in equilibrium. So we have the force that we calculate due to the increase of momentum, which is 1.4 Newton. So the upward force will be the same because the drone is in equilibrium, right? So the upward force is equal to the downward force. And what this law is called? Look at this, the name of the law that explains the relationship between the force in B, double I, and the force in CI. Newton's third law of motion, or law of action and reaction, like you guys learn in middle school. In order for the aircraft to hover at very high altitude, height, the propeller must propel the air downwards with a greater speed than when the aircraft hovers at a low altitude. Suggests the reason for this. Well, at high altitude, the density of the air is less, so that's why the speed is greater. This is the last section of this question. When the aircraft is hovering at a high altitude, an electric fault causes the propellers to stop rotating. The aircraft falls vertically downwards. Ouch. When the aircraft reaches a constant speed of 22 meters per second, it emits sound of frequency 3 kHz from an alarm. The speed of the sound in the air is 340 meters per second. Determine the frequency of the sound heard by a person standing vertically below the falling aircraft. So sounds like the Doppler effect. So we can use actually the Doppler effect formula to answer this question. So in the Doppler effect formula, you have the observer and you have the source. So the source is the sound source. So the sound source here emits a sound with a frequency of 3 kilohertz and is moving at constant speed of 22 meters per second at this moment. The observer is stationary and is going to hear a frequency of the sound because it's approaching, is going to hear higher than 3 kilohertz. So let's see how it works. So here is the Doppler effect formula. Fo is the frequency heard by the observer. Fs is the frequency emitted by the sound source. This V by itself is the speed of sound in the air, in this case in the air. And Vs is the speed of the sound source. So after doing all the substitutions, the frequency heard by the observer is 3200 Hertz.